As I said, today we are going to go to the Chinese restaurant for lunch. It turns out this membership assembly only is in the evening here, so it wouldn't actually have been necessary to move outside for lunch, but it's better to try to avoid any kind of problem. So, well, thanks everyone for being here again. The slides that I have are very, well, they're 37, but they're very basic text slides. So no fancy diagrams. However, I have some protocol traces that we can look at as well, and I can use since we have chalk now, I can use the board as well to explain some things as they are required. There was some interest ahead of OsmoDevCon in getting some kind of introduction into core network protocols, since quite a number of people, I mean, Dimitri of course knows everything that I'm going to say, maybe even better than I do, but of course there are a number of people who have worked primarily on the radio interface or on A and so on, and they don't have a detailed understanding of how things happen in the core network. So that's that was the idea, to have some introductory part, and as I said, there's not that many slides, there will be discussions and we can have lots of questions and so on. And then I have some slides about the different implementations that we have right now, different projects in OsmoCom that implement these protocols and what's their status and so on. Okay, well, as we all know, there is a number of core network components: MSC, HLR, AUC, VLR, EIR. EIR is really optional. The VLR normally is inside the MSC, and the AUC is combined with the HLR in many cases. So, and a lot of times when people say the MSC is talking to the HLR, then really the VLR is talking to the HLR, and the MSC is talking to its internal VLR. So the interface between MSC and VLR is not specified as not fully specified as an external standardized interface in the GSM spec. It's supposed to be some vendor-specific internal interface, most often between two software components in the same device. So that interface is never really specified. So it's always MSC together with VLR that then speak with AUC and HLR, which are also together. The AUC doesn't have any, I mean, nobody ever talks directly to the AUC except through the HLR. So even if an MSC or VLR wants to obtain authentication information, the request goes from MSC to VLR, from VLR to HLR, and then the HLR will contact the AUC. The AUC is never exposed directly to any other nodes than the one HLR that it is of that network. Well, I think the general functional split is known to most people. MSC is taking care of the call switching and mobility management functions. The VLR is mostly a temporary cache of subscriber data that it receives from the HLR, plus also maintaining and allocating TIMSIs. Sometimes also LMSIs, but we can ignore them, it's an optional feature. The HLR is the subscriber database, also has some subscriber location information, but location only in a sense that which MSC or which VLR the subscriber is registered to at the moment. AUC takes care of generating authentication tuples, and well, SMSC, we can skip that. Yeah, they're often integrated. Integration is so common that many of the graphs or diagrams you find in books or in other resources are actually, strictly speaking, not 100% correct, but I guess we can ignore that. Sorry? They all have some fancy names like CDE interfaces, but we can skip the details. The protocol stack that all of these core network interfaces have is the same protocol stack. It uses signaling system 7, or sometimes also called CS7, and the lower layers are identical to what you will find in a classic telephony, wire telephony system, where you have MTP level 2, MTP level 3 on the lower layers on top of an E1 physical line. Then you have ISUP used as the ISDN user part, which is the same protocol also used in fixed telephony for call switching. And then in parallel to ISAP, on top of MTP3, you have SCCP, the signaling connection control part. I'm not even sure about the name, and never really think about the name. Which handles routing and global title translation. We'll get into that later, what that is. On top of that, there's TCAP, and then we have MAP. So if you draw actually the stack somewhere, right? What you'll have in a classic stack is at the bottom you have your your E1, let's say a single time slot, 64 kilobits. Then you have MTP2, then you have MTP3, and then you have a split of either ISAP or SCCP, depending on the protocol. And then on top here you have TCAP and MAP, and then you have what's called an AS, an application server. That runs on top of the ISAP ends. There's no further protocols on top of ISAP, but that's sort of the classic stack that you find on core network interfaces. And sort of this part here is what you already use in ISDN core networks, but the SCCP, TCAP, MAP, and then the application server on top is new to GSM networks. SCCP in this context is always used in, I'm talking more about one of the slides. We have some elements in SS7 networks, they're called STP and SCP. So an STP, the signaling transfer point, is like a router for SCCP. If you think of IP networks, then that's sort of the router function. And it performs global title translation, which is key to routing in SS7 networks.
Do I understand correctly that SCCP is a kind of TCP?
No. Actually, it is, you could say, SCCP has a connection-oriented and a connection-less operation. So it's like, it represents a reliable in-order. You can run it in a reliable in-order mode, or you can run it in an unreliable mode. Actually, there are 4 different modes for SCCP.
Yeah,
2 connection-less and 2 connection-oriented. And if you think of it in terms of, actually, I think it has a lot of similarity to IP even, because that's you have the routing and you have address translations that you could sort of compare what's happening in maybe a NAT device on an IP level. So I think it's sort of a mixture between what you know in IP networks and as IP and TCP and UDP together. So it doesn't really map identical. So in this protocol stack, SCCP is always only used in connection-less mode. It uses just the UDT messages, which is unit datagram transfer. So there's no abstraction of connections, there's no like establishment tear down, anything, it's pure datagram transfer. However, I think it's operated, it requires in-order delivery. So TCAP, the transaction capabilities application part, requires in-order delivery of the datagrams. So it's a bit more than UDP. UDP is datagram. In IP networks, UDP is datagram oriented, but you have no ordering guarantee. But in this network, you have, at least the way how it's used by TCAP, you have ordering guarantees for it.
It's like SCTP.
Yes, but there you have associations that are explicitly set up, which you also don't have here. So, and SCTP, we'll see if we look into SIGTRAN, then there's all kinds of stacks where that gets involved. But basically, all I want to say here on this slide is STP is a transfer point, like a router, some kind of a node that passes messages left and right. And SCP, a control point, is an end node, like an MSC or HLR or any other node that originates or terminates signaling messages is an SCP. So not to be confused with secure copy. PC is also not personal computer, it's point code. Point codes is an addressing level that you will find on MTP. So there's different addresses at different levels. You have here you have point codes. PC is on this level here, and on this level you have as addressing type you have global titles. Point codes are well, depending on which it's the ITU or ANSI or whatever variant, they have different lengths in bits, but it's basically a couple of bits, like 14 bits or something like that, addressing on this level. And then global titles are like telephone numbers, you could say, that are used for signaling purposes. So a global title, this is just a 14-bit value or something like that. Here the point code. There are different even ways how to represent them that are completely look different, are completely incompatible. And on a lot of equipment, you can configure how it should actually represent the point code to you. This is weird stuff. It's not like an IP address where you know it's always 1 byte dot 1 byte dot 1 byte dot 1 byte. No, that would be too simple. SCCP really global titles are like telephone numbers. So you have in Germany you have something like 4930 blah 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 whatever for something that's located in Berlin. On mobile networks, it's typically they start with the global titles start with first you have the country code, so that's the CC, and then you have the NDC UR. Yeah, it's many years since I last used JAWS. It's good. NDC, the national denominator code, and let's say, for example, in E+, I think it would be, sorry?
177.
177, yeah, exactly. So this is one German operator. So let's say you have a global title of an HLR of E+ in Germany, then the global title starts with 49177, and then you have more digits, like in any other telephone number, you have more digits towards the end. That's how global titles look like. There's no plus in front. That plus is... Jolly has enabled the camera so he can see what's happening behind. Cool. So, okay. Furthermore, we have subsystem numbers, and that's like, you can say a little bit like port numbers in the IP networks. And the subsystem number identifies a logical function like an MSC or an HLR or something like that. So you can address basically any entity, any SCP you can address by a global title plus subsystem number or a point code plus subsystem number. There's different types of addresses that you can use, and they get translated between each other at STPs. So what is this global title translation? It translates a destination global title into a new destination address. So let's say you send a message and it has one global title like 491770001 or something like that, and any STP that receives that message can now have routing tables where it looks up the original destination global title and then determines what kind of new address it should put in the packet. So it's not an end-to-end transparent system where the addresses don't change, but intermediate signaling transfer points, there can be any number of them, can rewrite the destination address to make sure it goes to the right destination. And this new address can not only be a global title again, but it could also be a point code or subsystem number or any combination of those. And then it will send it out again to the signaling network to the final destination. So if you compare that to IP addressing, then first of all, instead of just having an IP address, you have 3 different or 4 different addressing types. So you can have different addresses at SCCP level, and also all these intermediate routers, aka STPs, they rewrite the addresses at will based on a local configuration that is the global title translation rules. On MTP level, as I said, it always works with point codes. So Let's say you have some higher level application, you have you have some application server here, like your MSC, and it wants to inquire or get authentication tuples for a certain subscriber. Then it puts in the destination global title. It sends it down here. It sends it down here. It sends it here, and then what will happen is between SCCP and MTP, a routing decision is made to which MTP3 link should the SCCP message be routed if you have multiple links. So from the global title you map onto a point code at MTP3. The point code in MTP3 determines at which other node in the MTP network the message will reappear. So you have at MTP3 you have lots of different nodes. It will reach at the destination MTP3 node. And at the destination MTP3 node, it will get passed up to the SCCP layer. And if it's an STP, then inside the SCCP layer, you look up the destination global title, you do your translations, and then you send it down to MTP3 again, so you can again route it to another STP or to the final SCP. So there is global title translation at SCCP level, where you really map from one destination address to another on this level. And then also there are routing decisions when SCCP passes messages down to MTP, as any node can have a number of MTP links. So basically you have two levels of routing or two overlaying networks. One is the MTP-based network where you route on point codes, and then overlaid on top of that you have an SCCP network where routing normally is based on destination global titles until you are very close or at the final component where maybe it will only be routing based on MTP or on subsystem numbers. So very strange concept. I mean, all kinds of historical explanations, but
from your experience, all these rewriting possibilities, are they actually used in practice?
yes, all the time.
How do they debug these networks?
I'm sorry,
Yeah.
may I interrupt a little bit?
Of course.
To explain the reason. So it's not, there is no pure MTP network. There is a set of networks, huh? So, and the one MTP point can't address directly another MTP point. So they are grouped into networks. And the CCP global title translation is required to operate as a NAT, maybe, between MTP networks.
Am I correct that MTP networks, MTP links are all only point-to-point links?
No.
No?
But there are, I think, it is maybe necessary to add that addressing on the MTP layer is done by means of point codes plus network entity. There are three types of networks: national, local, and international networks. And the MTP address can be addressed point. So you can imagine you have your own private network, which is divided from outside world by means of NAT. You have 192, 168, etc. network inside. And in order to reach another destination, you are always using NAT. And this NAT in the SSL world is SSP global title translation. To NAT between networks, MTP networks.
So maybe just I try to draw out something really quickly. So let's say this is the German MTP national network, and you have a variety of MSC data, whatever kind of things that are connected to the network. So you can, as a German operator, you can go to the regulatory authority and you can have them allocate point codes for you, national point codes. You get some national point codes, and you can allocate them to either STPs or STPs, whatever in your network. Typically it's only to STPs, but just to simplify, I said it's for STPs. They can directly talk on MTP3 level between each other, and they don't need direct links altogether. There is routing in MTP, but you can only address other nodes in this network that have that also share or have a national German point code. So there's one address space in here for point codes, There's another address space for international point codes, and then maybe that's in Russia, there is another national point code network. And there's another third hierarchy that he said for private point codes, but I didn't introduce it to make it not too complex. It's the same principles. And then you have STPs that are connected to both, so they have a connection with the national and the international MTP networks. So this is called an international gateway. And in order to reach some node that only has a Russian point code in the Russian national address space, you have to sort of first know that you have to send it on MTP level to the international gateway that connects the German point code range with the international point code, not range, but point code address space. So on MTP level, this is the source, this is the destination, when you send the first message here. But on SCCP level, you put in the global title of that node over here, and then the SCP here, based on global title translation rules, will know, oh, I need to send it using MTP, but a new MTP source and MTP destination point code in the international point code range to that STP, which then again looks at the destination global title and then knows, okay, I have to send it to such and such point code here. So that's sort of roughly how it works. But there's global title routing, and then there's also global title translation where you rewrite. And the translation is used all the time, every day. For example, in the case of the mobile global title, that's sort of a special case. So if you go into any GSM network using your mobile phone, like you here with your, I don't know, American, Russian, whatever GSM phone, you switch it on in Germany, then when the phone registers, when it performs the first location update, the only information that the visited network has is your IMSI. So the phone sends the IMSI, and let's say it's a Russian IMSI. I actually don't know what's the country code for Russia in GSM.
250.
250. So let's say it's 25001, it's the first 5 digits of the IMSI. And what the MSC then will do is it will replace that 25001, the IMSI, into what's called an MGT, a mobile global title. And in the mobile global title, the 250 gets to 7, I think is the country code for Russia? 7, right? Yeah. So it becomes 7, and the 01 gets transformed into the national denominator, the NDC for whatever is that operator in Russia. And the remaining parts are just copied into the mobile global title. So there's a mapping how from an IMSI you can map onto a global title, which is a special global title that's called the mobile global title. And then that will be the SCCP destination address for the HLR. And then some STP somewhere will map from that sort of IMSI-derived mobile global title to the real global title of the respective HLR. This is done so that not every operator in the world needs to know what is the HLR of every other operator and somehow maintain tables. But basically, let's say this is whatever. What would be an NDC in Russia?
I'm not sure that it's necessary to translate INSI into UE164. I think INSI is used as a global title here. I'm not sure.
No, it's really the mobile global title, and it has a different address, different.
Translation type.
Yes, it has a special type, but still there is a translation happening because all the global title translation rules, they only work on country codes, not on mobile country codes. So there's a translation from that and that into an NDC, and then the message gets transported by the SS7 network. So every time somebody in a roaming case makes a location update, every time there's global title translation involved, and there are many other cases, but that's for GSM a very, very common case where these address translations are actually used.
Are these routing and translation tables more like static configured?
If you're establishing roaming agreements, there is a special form, so-called MT21 is
Yes.
it may be a mistake here. So where you are announcing a lot of stuff such as global title, IMSI range, numbering range, class, camel, etc.
Yeah, but this is a real form on paper.
Yeah.
So you submit a form and on paper to the GSMA, which then distributes it to all the other GSMA members, and then some slaves are sitting at all the consoles and hacking in new entries into the
Point to point
GTP.
form.
Sorry?
It's point to point form.
Oh, it's point to point, really? Ah, I thought it was distributed. Okay, even worse. So it's not. It's not.
There is no BGP.
No. That would be way too.
It's money.
Yeah, there are actually people. I know some people that do nothing else but freelancing MSC configuration services.
Yeah.
So it's like somebody, just imagine. I mean, of course, we have all these Cisco experts, but sort of that's more. You make a certificate and work for an operator, but there are actually people who freelancing do nothing else but enter rules in MSCs and STPs and so on.
There is a separate business from Kubernetes. So there's a person who are reducing the stuff from you. So if you are a tiny operator, you can do without direct links point to point. So if you're starting your own cellular business, you have to travel about 100 countries to get at least a single roaming agreement in each of them.
Yeah, there are even virtual roaming hubs and all kinds of strange things. But let's get back to the basics, though, before we get caught up in details. And yes, that was a good idea. Okay, so the physical layer, well, traditionally it is really E1 time slots, either a single time slot or multiple time slot, or there is also a way how you can use the entire 2 megabit E1 link for signaling. That's the high-speed signaling links, this 2 megabit. And on top of that you have MTP2, MTP3. A lot of modern networks, not so much yet on the international interfaces or the interoperator interfaces, but internally at least they use a lot of SIGTRAN. So the idea is that you use IP-based networks as a layer that replaces these legacy E1 lines, and then you use SCTP as layer 4 protocol instead of TCP or UDP. There are many different stacking options, and then there are also proprietary protocols like SCCP Lite. These are the different SIGTRAN stacking models that are available. So either you can have IP SCTP, then SUA, which is the SCCP user adaptation, then TCAP and MAP. That's sort of the simplest stacking, but the most seldomly used one, at least based on my experience. Huh?
It's a fairy tale.
No, I have seen it in use, but yes, but not, not commonly. There even was a TUA at some point, but it never made it an IETF standard. In that case, even it would be just MAP, no TCAP in the picture anymore. But that is really a fairy tale. So then you have M3UA, which is the MTP3 user adaptation. So user adaptation always means the next level protocol is normally a user of whatever you're adapting. So on SUA, you have TCAP because SUA is an SCCP user adaptation, and on top of SCCP you normally have TCAP, and that's why this stacking. M3UA means MTP3 user adaptation, so you don't have MTP3, you have M3UA, but then SCCP on top because SCCP is the user. This stacking, M3UA, is more commonly used, and because it allows also for SCCP and ISAP on the same signaling links. Because in the last stacking, if you have SCCP user adaptation, then of course it's only valid for SCCP users. But ISAP lives in parallel to SCCP, it's not a user of SCCP. So in the last stacking you cannot have ISAP, which makes it somewhat limited. I mean, you can use it for an HLR or something like that, but you cannot use it for anything that relates to MSCs, because they use ISAP for the signaling. Then there is MTP2 user adaptation, where you don't have MTP2 but M2UA, and then MTP3, SCCP, TCAP, and MAP. And then you have M2PA, which is the MTP2 physical adaptation, where you actually have MTP2 and MTP3 and SCCP and so on. So the first line really is a full MTP link over IP, So you have MTP, all the protocols that you have on an E1 line, you have on inside SCTP over IP, and the other ones are sort of more simple in case you don't really have to want to have a one-to-one mapping of classic signaling links. So there are all these different stackings, which makes it particularly exciting to support SIGTRAN. It's like, yeah.
Is there any real use for the first two?
Yes, yes. Actually, they use quite a bit because if you have an existing MTP network, then the first option is closest to what you have been using so far, because it has all the protocol stacks identical to what you had on E1. So if you just replace an existing MTP link over E1 with a SIGTRAN link, then it's very likely that you will use M2PA or maybe M2UA, but those ones. The other ones here, the lower two, they're mostly used for connecting like an MSC server or an HLR server to an STP. So only for the last part of the system. To connect the actual like HLR or MSC to the STP, and then the STP may continue over E1 or whatever, depending on where you route it to. So it's like different use cases in those options. Okay, well, SCTP we already discussed to some level. Yeah, the various different stackings make it sort of a bit, sometimes a bit of a challenge to make things interoperate, because especially on the marketing level or even the selling and buying level, oh, this has SIGTRAN, let's buy it, and then you say, okay, this one does M2PA, this one does M2UA, and it still doesn't work. So you need again something to translate in between. It's quite funny. Also, I know even very cheap. I mean, to get some idea about this, if you want a commercial high-end SCCP stack that supports more or less all of these options and all of these protocols, you can pay something like $50,000 per year in licensing for a single installation of the stack. That's sort of the higher end price. There are cheaper ones, but this is if you want something that Ericsson developed. Then now it's maintained by a different company for some years, but actually Tieto, where Martin...
Good business.
Sorry?
It's a good business.
Apparently, yes. Especially since this stuff is all not new. So it was developed some years ago, and I'm quite sure all the R&D expenses have been recovered at least 10 years ago. So it's really just maybe porting into a new Linux kernel or something like that. Yeah, so this is all very expensive stuff, and quite often even you have to pay for the individual SIGTRAN options. So I recently was involved in a project with a customer where he had to pay something like $5,000 extra to have M3UA. And again, single installation, right? It's not for some global kind of, but for a single instance, a single license for a single node. To have M3UA. I mean, all the other stackings, several others were there, but he needed M3UA, and he should have paid that. So I put some of my Erlang code to translate. It was considerably cheaper. So SCTP we already discussed. Now, what is TCAP? It's the Transaction Capabilities Application part. It's the idea to decouple some transaction notion or transaction logic from the actual application that you use. So if you look at mobile networks, basically everything you can think of as a transaction. Location update is a transaction, you know, sending an SMS is a transaction. It involves certain steps, and at a certain point it's terminated, so you have some kind of transaction logic. We do not have any connection orientation in here. So you could, theoretically, you could say, well, we don't need TCAP, we just establish TCP connections all the time and then talk map over those TCP connections. On a very abstract level, you could think like that. But then you would have to set up a full connection all the time. So they did not want to use connection semantics in signaling networks, because setting up a connection is a very costly operation involving several messages like three-way, four-way handshaking and so on, and that's not useful for the signaling network. On the other hand, a pure datagram-oriented system doesn't give any kind of, you don't know has the transaction completed or not, you don't know whether the message has reached the destination, so it doesn't give you enough. And a transaction protocol is sort of between a pure datagram protocol and between, on the other end, a full connection-oriented protocol. It's in between. It does not add as much overhead and as much interchange and messages exchange than a connection, but it provides you this guarantee that either it will succeed or it will fail, or you have some you don't end up in unknown states.
So it's like SIP actually. So SIP usually use UDP for the same reason.
Yeah, but then inside SIP you need to take care of retransmitting stuff and and all that. And the idea with TCAP basically is that you remove and generalize that part out of map or any other user like camel, cap and so on, and you have one sort of generalized way of handling all the different failure cases and that kind of concept. Has also some other features, so you don't have to implement it each and every time you define another higher level protocol.
Okay. Yeah, so this looks like a good idea.
Yes, it is a good idea, however it's horribly complex the way how they did it. If you look at the specification, it's dozens and dozens and dozens and dozens of pages full of SDL state diagrams that show you something like 14 different state machines and how they interact with each other and so on. It's can be a bit challenging, but I also think yes, the idea is good, and maybe just the implementation a bit more complex than it should be, because they have actually split TCAP in two parts. One is the TR part, the other one is the TC part. So one is a component and the other is a dialogue sort of part, and so how can I say, they split the functionality of TCAP into two sublayers, and in the spec it states sort of that, well, the only user of the lower sublayer is the upper sublayer. So it actually defines the primitives between the TR and the TC part, even though the TC part is the only thing that will ever use the TR part. So lots of interfaces and interaction that maybe could be done much simpler. I've seen some people in the academia publish papers where they they entered all these SDL diagrams into some kind of machine, and they sort of tried to reduce it into a simplified set, and they didn't publish, of course, the new result because they probably wanted to sell it, but they were able to, with using automatized tools, they were able to mathematically prove that you can achieve the same with much less states and much less state transitions and much less state machines, which still behave exactly the same way. So,
but it's a good work actually.
Well, yeah, but as I said, it's not released, neither the tool nor the result, so very unfortunate. Okay, now map is what's used between all the core components. Oh, by the way, I didn't mention that ASN1 TCAP messaging is specified in ASN1 and uses basic encoding rules. And the same is true for map. Map is then the application protocol that's used on top of TCAP for GSM. In map you have location update, MOSMS, MTSMS. You have inter-MSC handover of calls. You have updating of subscriber informations, cancelling location information, and many operations.
So inter-MSC, I just mumbled it as another fairy tale. Inter-MSC handlers.
It's not a fairy tale.
Oh.
There are even operators that have inter-operator inter-MSC handover working.
Okay. Every time I cross a bridge in the San Francisco Bay Area, my phone calls. Not the lack of coverage.
Actually, I'm surprised at how badly US GSM networks works. Because, well, I have in US I have troubles with GSM networks much more frequently than in Russia. So when I was first in the US, I was just surprised because I think that well they have networks for longer time, then they should work better. But call drops, SMSs are not delivered, and all kind of crap. So.
Maybe speaking about US case, I think I know NCSS7, but I can't realize how GSM works with NCSS7.
ANSI, yeah, I have no idea. I never looked at ANSI.
I can briefly explain the difference, but I have no idea how MAP is working on these days.
I know it does, but I have no idea how. Yeah,
So there are there is no global title translation at all.
Interesting.
So point codes are 24 bits,
Hmm.
and it means that all the network hierarchy can be shown and can be touched with this 24 bits.
Hmm.
So the first 8-bit decides, so each level of hierarchy is the next 8-bit sequence. And if in the case of map, application layer determines the type of global title translation. And normally numbering in some way is used for routing. In IS-41 is some sort of an analog for map. In US world used for AMPs, for CDMA, etc. So it uses directly point codes from application layer. That's okay for IS. I'm sorry, I made a mistake. So it's okay for American-based mobile systems, but it has nothing in common with GSM. And for example, if you have to mix sublayers from different stacks, and this is the real use case for example, if you are using AMPs in Europe, if you are using US CDMA in Europe, and there are cases. So all the lower levels, normally MTP up to MTP3 or SCCP should be YETC based, not yet, sorry, ITU based, and upper layers are from ANSI. TCAP in any case, and application line for sure. And so there are special tables to convert point codes into global titles. Otherwise, it's impossible. Or to convert 24 bits global titles used for application into 4 bits plus network indicator. So another type of translation. But in the case of map, that requires real global titles, kind of major.
I'm not sure how they do it. As I said, I just know it somehow it works, but I don't know how they implement it. And as I said, honestly, I mean, if somebody has an interestingly large enough project, then I will look at it. But otherwise, I don't. I personally, I'm not interested in the NZ world.
I've heard there are sophisticated roaming gateways for these purposes. No idea.
Yeah. Okay, we're going to look at some examples of the protocol stacks soon. I just want to say map and cap, and then I can actually show you some protocol traces. So, as that map is for GSM mobility, and there is cap for camel, which I'll also talk briefly later what camel is and so on. It's very similar to, I mean, encoding wise and on a layering point of view, it's just like map. It's on the same level. It's just a different protocol, another protocol that uses TCAP and STCP and all the lower level parts together. So let's let me try to find the trace. I knew there was one somewhere. There we go. So this protocol trace was downloaded from 4Shared, and it's from 4Shared website, 4shared.com. It's a file sharing website. And there's a government-owned Indonesian operator who for many months uploaded every day real-world HLR, gigabytes of HLR protocol traces to a public 4Shared account that was not read protected. So, why? I guess the employees were exchanging files that way. They also had daily performance reports from their NSN, OMC, and so on, showing how many call drops and all the information that any competitor would always want to see about their network performance. This was all public. Every day there was new.
They don't care about competitors. It's Indonesia.
Well, I'm sure they have competitors, but anyway. So this is a real a trace taken from one of these HLRs. You can see probably there should be timing. Yeah, April 2010 was that. The capture, and this is in a SIG-TRAN protocol stack. So you have Ethernet IP, and then you have SCTP, then M3UA, and actually you see multiple SCTP chunks here. This is a highly loaded network, so it's not just a single message, but you have, in SCTP you have chunks, like data chunks, and actually multiple of these chunks in one SCTP message here. So we have M3UA, so it's, as I said, in this case it's an HLR trace, if I'm not mistaken, and they use M3UA as the adaptation layer. You see a routing context that's, well, something that M3UA and SUA use. You can sort of have something like multiple virtual links inside one M3UA connection. I think we can skip the details here. So, as a payload inside M3UA, it just says protocol data, and it tells us this is SCCP protocol. You have an origin and destination point code, and you have a network indicator and signaling link selector and some other fields that Wireshark can also translate then into how they would look like in a real MTP3 message if it wasn't M3UA. But I think that's just some header fields. We can skip those. And then SCCP is where it starts to get interesting. So we see some unimportant information, but then we see the called party. The called party subsystem number is HLR, so this is a message that's being sent to the HLR. Address indicator tells us we should route on SSN, so this is the information we should route on the subsystem number, which is the HLR. The global title of the HLR is this one here, 625 and so on, Indonesia, as Wireshark recognizes it. That's the global title. So plus 62 or 628, I think plus 62 is Indonesia, so it's really an Indonesian global title here. Then we have a calling party who is actually talking to us. It's an MSC, and the MSC is also an Indonesian MSC that's talking to us with a different global title. So this is the global title information on SCCP level, and if we go in TCAP, we will see TCAP consists out of components and dialog part. So first of all we have a transaction identifier to identify the transaction. This OID tells us it's some TCAP, and actually in turn I don't remember exactly why it is in there. And then we see it's a dialog request. Somebody tries to establish a dialog. The application context name here tells us a short message gateway context, version 2, so related to an SMS transfer. And in the component portion, we then have an invoke component. An invoke is sort of, reflects the two layers in TCAP. There is always the dialog part and the component part, or the transaction part and the component part. And you can have multiple operations or components that are invoked inside a single TCAP dialog. The only place where I have seen this in use is in the location update, but I'm not sure if you know any other case.
You know, if you're trying to route short messages from SOC, the normal case you can apply directly to HLR and all. So you can unite these procedures while delivering short messages. So unite the procedures of getting the routing information and delivering messages.
Okay. Yeah. But the other case, the more common case that I'm seeing is in case of location update, where you have actually two nested transactions inside one dialog. I will show some ladder diagram to illustrate that. But just to show you, in the TCAP layer, now we only see we see the application context name. We see this is invoke ID number 1. The operation code is 47. It doesn't know what that is, and then we see a constructor tag and some. This is just the ASN1B RD code without knowing what it is, because the TCAP layer doesn't know the content of this. It just knows, oh, there is some stuff inside, but I don't know what it is. And then we have to check in the map layer, where we see, well, invoke ID 1 and 47 is report SM delivery status, so short message delivery status. Then we see there's an MSISDN inside. So again, the Indonesian international MSISDN, and the service center address, the SMSC that's involved in that, and the outcome absent subscriber. So the subscriber is not there, was not reachable. That's sort of what you can see in this particular map transaction. And then you see there's some other transactions going
Is
on.
that invoke ID the same as from the TCAP?
Yes, it's the same.
It is the same data.
Yeah. So
Just decoded on the layer.
on both sides, yeah. So in TCAP you have a dialog. The dialog is identified internally on your software stack. It's identified by a dialog ID, but on the wire it's identified by a transaction ID. And the transaction ID is actually, there's a source transaction, origin direct transaction ID, and destination transaction ID.
It's convenient. It's really convenient. For example, if you are originating a transaction, originating transaction ID is nothing but a pointer inside your stack.
If you have 32, it can actually be more than 32 bits. But
It's
probably
up to you
it's only 32.
how to code it. You can hash it or whatever. But it's in reality it's a pointer. And again, if you're receiving a transaction, you can use your own pointer on your side. You forget about the link number.
Yeah, okay, that's one option how to use it.
And the same in SSP.
Yeah.
SSP connection identities, it's exactly the same.
Yeah.
So it's all bare metal programming.
Well, you don't have to. I mean, the spec just says it has to be a unique identifier that's chosen by the source.
Yeah, but I mean that I think it was inspired by bare metal programming.
At that time, possibly still yes. Yeah, I think today, if you look at implementations in higher level languages, and of course you don't use that. You don't use physical addresses or even logical addresses. Pointers.
When that address comes back to you, when that transaction ID, when a message comes back to you, it's part of that same transaction.
So these two numbers are linked. For example, on the if you're an originating side, you're choosing your number.
Sure.
Then when this message is, when you get the response, another number is tied to it.
Right, but when you get that response and you look in and you see the transaction ID from your side, the one that you generated, you're saying that in some implementations, they probably pull that transaction ID out and use it directly as a pointer.
But you should check it.
You should, and how can you check it, I mean, do you know?
Yeah, but that means, we can basically corrupt your stack from the outside just by sending you a message with a weird number in it. That's
But you should check also, it's not a pure pointer, so in any case you should verify.
Yeah, okay.
It's not a pointer, it's index.
Okay.
Well, okay. So, just as I said, to show some of these messages, I mean, for example, let me see if we can find some. Yeah, invoke update location. Oh, there's actually some decoded problem here. But let's look at. Yeah, this is an update location. So this is just to show you the most basic transaction that everyone knows. It's update location request with an IMSI. and you see the MSC global title from which this update location request is coming, the MSC, the VLR global title, which is identical here in this case, and yeah, LMC, that's not really necessary, like a local subscriber identity, and then some VLR capabilities and some stuff that Wireshark cannot decode. But here, for example, the MSC that performs the location update to the HLR tells the HLR what kind of camel phases it supports. And get to camel phases maybe a bit later. It's what we can say what version of the camel is supported, or what feature set inside camel is supported by this MSC. Gets sent back to the HLR here. Okay, now let's look at some ladder diagrams. I have to find them. Just give me a second on these. Yes, so this is a full, actually for anyone who is also preparing some presentations or slides, I can strongly recommend my Gen Ladder tool. So, because you get really bored in drawing these kind of diagrams, and I hate if I hate anything, then it's graphical stuff. So, especially it's time consuming. So, I have this text file where you say what kind of messages go between which nodes, and you define the nodes in the beginning and their names, and then you define all the messages. And then there's a script that generates this graphic from the text file. So,
And so what's the tool? How this tool is? What's the name of this tool?
Gen Ladder, GEN_ladder. It's on Git OsmoCom.org. It's a small Perl, I think, program, if I remember correctly. Yeah, it's a Perl program. So this is the location update process, including the core network. So this part, of course, everyone knows, RAG first, then this is ABIS for those who do ABIS, like channel required, activate request, activate acknowledgement, immediate assignment command, blah, blah, blah. Then we actually get I didn't show layer 2 here, LabDM, right, but it's the location update request, which from the PSC over the A interface gets sent as a complete layer 3 information location update request. By the way, the font is scaled automatically by the script. I didn't have that in the first version, but it was required soon later.
Is there an option to instead wrap lines?
I don't think so, but I'm happy to accept your patch. Then what the MSC does is it sends the identity request. This is the first location update in a roaming case now. And there, maybe the location update request is done with TIMZ, and then, but we want to have the IMZ, so we send an identity request IMZ, we get the identity response. And then what happens is that, again, this is MSC VIA, it's HLR AMSC, so we get a map transaction send authentication info to the HLR, which then talks to the AOC, and then we get authentication info response. This is our authentication triplets, or in case of 3G authentication, the authentication quintuples that get returned here into the VLR. At this point, the MSC VLR is capable to do the authentication request. Then the phone responds with authentication response, which, if the authentication succeeds here in the MSC, it will trigger a map update location area request to the HLR, which will trigger an inverse transaction, a nested inverse transaction for inserting subscriber data. This is basically the HLR sending more or less a complete dump of the subscriber record into the VLR. And once the insert subscriber data is confirmed, the transaction is confirmed with insert subscriber data response, then the original location update request transaction terminates. So you have two nested transactions, and the second one is inverse direction than the previous one. And they both happen in one TCAP dialog. So you have one TCAP dialog, but two transactions, each of them identified by invoke ID. So you have two different invoke IDs in one dialog ID or one transaction ID. After that point, since the location update area was correct, then a good MSC will start encryption, and that will propagate to the phone. At some point we get back the ciphering mode complete. Oops, scroll that. The location update response gets sent back to the phone. So this is what happens in the core network in the first location update. If you look at the follow-up second location update, then that's I ignore the BTS and DSC part in this diagram to simplify it. So here we already, we get the location update with the TIMZ. The TIMZ is known in the VLR, so then we send, okay, this is actually, sorry, yeah. So this is when you do a location update because you have changed MSCs actually. If you have moved from one MSC coverage area, one VLR coverage area into another one, what happens, you have a new VLR, the old VLR, so you get location update for a TIMZ. The TIMZ is not known here. The new VLR sends a map transaction to the old VLR to send the authentication tuples and the IMSI belonging to that TIMZ from the old VLR into the new VLR. And then you have transferred that information to the new VLR, so the new VLR can do authentication.
Doesn't it first have to ask the HLR for routing information? Or
How does it know the old VLR?
Or the old VLR?
There are two different ways. I remember there are two different ways.
Does it have
Some MSCs actually, or some VLRs have local tables that map from location areas to VLR identities, so you can skip contacting the HLR.
And so location update contains the old location area? Okay.
Yeah, and then you can have some MSCs have local tables where they basically you have the neighbor VLRs and their location area code ranges, or you've configured them so you can do it directly without going to the HLR first.
Okay.
So sorry that it's not indicated here, but good question, very good question. You almost got me. Then the update, that's the same. What's new then here is that there is a cancel request. So as soon as the HLR gets the new location area request from the new update location area request from the new VLR, it will send a cancel location request to the old VLR so it can remove that subscriber record from its database. That gets confirmed. Then it will insert the record into the new VLR, that will get confirmed, and then the location area update completes at that point.
Yeah, the maps and the identification. So the old MSC sends new authentication templates he has himself to the HLR, or the old one he used the last time?
No, but the way how it works is when an MSC or VLR requests authentication information from the HLR, you can request a number of them, typically 3, 4, 5 or so sets of, so you don't have that transaction too often. And once you have used one of them, you remove it. But there may be some leftover already computed authentication tuples, and those leftover tuples get sent back get sent to the new VLR to reduce the amount of load on the HLR and AUC for those requests. But once it has been used once, the spec clearly says it should not be used anymore. It should be removed. Yeah.
So it's a very convenient transaction of standard identification, So there are several use cases, very non-traditional use cases where it can be used. For example, if you would like to make welcome SMS inside a local area, inside some base station, you can see it on the TIMC. But TIMC allows you to deliver messages without any stuff. So this allows you to translate TIMC to TIMC if you know to whom this particular base stations belong to.
Okay, yeah. Okay, but of course, as I said, map is not only used for location management. You also have for example, mobile terminated call in a roaming case, just to see what kind of transactions happen here. This is mixed map and ISAP transactions. So the beginning, let's say a mobile terminated call. So from a landline network, or for something that looks like a landline network, you get an ISUP IAM initial address message. No, I always forget the acronyms, especially when it comes to camera. I never know what all these acronyms mean. So yeah, with the MSISDN, of course, ISUP works only on MSISDN. So you get that. It goes into the gateway MSC. The gateway MSC. How are we in time, by the way? Okay, yeah, should move quickly. So send routing information for the MSISDN to the HLR. The HLR will go to the visited, as I said, this is roaming case. So VMSC means visited MSC. So VMSC and MS is in one country, the HLR is in another country or another network, and that is coming in from the landline. So the HLR will then send a provide roaming number using the IMSI to the visited MSC. The visited MSC will temporarily allocate what's called an MSRN, the mobile subscriber roaming number. It will return the MSRN to the HLR. HLR will forward that MSRN to the gateway MSC. So there's the send routing information response, SRIRES, with the MSRN. At this point, the gateway MSC knows to which kind of mobile subscriber roaming number it can forward the IAM message. So it gets forwarded to the visited MSC in the visited network, which can then generate call control setup and do this standard GSM layer 3 call control signaling. Gets confirmed, then it's alerting. The alerting will trigger an ACM. What does ACM mean? Anyone remember?
Address complete message.
Address complete message in ISUP back, that gets sent to the gateway MSC and gets forwarded to the actual caller. Once the caller picks up GSM CC Connect, gets sent to the visitor MSC. The visitor MSC will then ANM, the answer message, I guess, and that one gets again forwarded. And once in this case the A caller hangs up, there's a release message that gets forwarded and gets released over here, and regular release complete. But you see also here there's some map messaging involved in this transaction in the beginning. Let me see if I have some MO call roaming. I think I even have, let me see. No, this is not good. So this is in a mobile originated call in the roaming case. So the channel establishment, maybe we need to request some authentication tuples if the VLR doesn't have any leftover authentication requests, ciphering, then we get the setup. The setup will go directly to ISUP. There is no map transaction involved here anymore because it's mobile originated. We don't need an MSRN or something. The MSRN is only required in mobile terminated case. Well, then we have the regular ISUP transactions here, so it's not as exciting. These are all non-camel cases. This is classic.
It's completely fairy tale. In non-camel case, there must be either USSD or whatever to get real money, real online money, online billing.
Yeah, but I mean, in prepaid cases, yes, but for postpaid cases, it still works like that.
It's really impossible. It's a fraud. Guaranteed.
No, but this is how I see it in real world networks, in non-camel case.
Without any USSD or whatever. Without camel or USSD.
Yeah. I think camel or USSD only in the prepaid case.
Yes.
Yeah.
Yeah,
I'm talking about postpaid.
yeah, in Europe there are a lot of postpaid users. So.
For a postpaid user, you should have a mechanism to check the balance. Postpaid.
No, you have no way to check your balance in a postpaid.
Until the month ends.
Postpaid is just a model of interacting with the customer. But postpaid means that you have a credit that you can allocate him and operating in the same way as prepaid does.
No. In Europe, it's really post-pay. You can get a single month phone bill with 20,000 euros. There is no limit.
In Russia is not that. In Russia you can check your balance if you are postpaid, so you always know your balance. It's just a matter of when you pay, before the call or after at the end of the month.
When you are buying a credit, moving to Vietnam or whatever, providing free services for anyone, long distance calls, throw it away and forget.
What do you mean?
But to get such a postpaid card here, you have to identify yourself, and you have to have good credit to get one.
You can, so there are ways, and it's not a technical aspect of how to get credit SIM card.
Yeah, but that's if it's a SIM card with credit, it's a prepaid card. But we are talking about a postpaid card. You go to a store, you identify with your ID card. You will not get it without a passport or ID card, and they will do some check with your
Stolen
bank.
passport or whatever.
Sorry?
Stolen passport or whatever.
Yeah, but then you would have to put somebody else's picture inside. And also they go beyond that. They even make an inquiry with your bank and so on. But yes, if there's identity theft, sure, but it's not a GSM problem.
There were huge amount of real cases for this sort.
One time I was in the US, and I don't know, after a few weeks my operator called me and said, hey, you run up already 2,000 euros of roaming charges, are you aware of that? So,
Yeah, I mean, postpaid accounts are standard in the United States, so in fact, I get it when I am traveling internationally, I get a text message from my operator every day telling me how many roaming minutes I've run out in the last, 24 hours.
Okay, one more question. Who inserts the MSISDN? The NSC?
Yes.
Okay.
So at some point you will have had a location update before this, of course. Otherwise you couldn't.
Yeah, the DLR and those.
Yeah, exactly. Yeah. Okay, then let me continue. Let me just check the schedule we had until 1. Okay, so
One more question about Invoke IDs. If I start a supplementary service from my phone and the phone selects an Invoke ID, is that Invoke ID then also used in TCAP?
I don't think so. I mean, it may be, but I mean, it's an implementation detail. I would say it might be possible that some do it that way, but I mean, what the TCAP stack needs to make sure is that the invoke IDs within one transaction are unique. That's all it needs to care about. So you never have multiple different phones inside one TCAP transaction, so you could theoretically reuse it. But on the other hand, why you have a special case if you always have to have invoke IDs, one local invoke ID namespace per transaction anyway, or per dialogue anyway, then why make a special case for supplementary services and then use something user provided in that case? I don't think it makes sense. Okay, Camel, yeah, as I said, can talk about this later at some point. Now, roaming interfaces, there's not really anything specific to roaming interfaces. You have the SS7 stack, you have ISAP, MAP, and CAP interfaces. And for GPRS, you of course have packet data interconnection, normally GRX connection to connect your SGSNs with other operators, GGSNs, and vice versa. But classic GSM, you only have ISAP, MAP, and CAP interconnection. And of course, you have to have the roaming agreement, which, so they are all bilateral normally, so it's like a mesh of operators, each having contractual relationships. There are some roaming hub operators that act as intermediaries, but still it's lots of peer-to-peer, point-to-point agreements. So in roaming, what happens is you have the MSC, VLR, and SGSN in the visited network. So PLMN, public land mobile network, I guess everyone knows, and we visited. And the HLR, AUC, GMSC, and GGSN are in the HPLMN, home public land mobile network. They talk to each other using map, just like in a non-roaming case. So there's not really any difference. The only difference may be that you have inside your own network. In a non-roaming case, you only use point codes or even subsystem numbers to address equipment. In a roaming case, you will always have to use global titles because otherwise you cannot reach the other operator. The selection of the home public LAN mobile network is based on the IMSI. That's what I said with this mobile global title, the E212 translation. Title case. Yeah, so in the non-roaming case, they are just the same network, and that's sort of it. Well, MVNO is just a small slide. It's sort of a special case of roaming where you have an MNO that operates has a RAN and core network, and the MVNO operates the home network without RAN. So it's like a roaming case, but with an operator who doesn't have any radio access network. So you have an MVNO that only has a core network but no radio access network, and you have the MNO, the real operator, which has a core network and radio access network. So all the subscribers then sort of roam in the MNO network technically. So it's just like the regular roaming case. There's nothing really special about the MVNO.
Actually, I should say that this is a little bit different. Maybe it's just country difference. In Russia, we have a definition of MVNO based on the spectrum license. So the company without spectrum license is MVNO, no matter how it uses the network. Because
In Europe, it's used service provider. It's in European case they are called service providers, not MVNOs. So
yeah, so in Russia, I think it's just written in a legislation that MVNO is a company without the spectrum license. So it somehow have to have a partner with spectrum license. So in this case, it's named virtual network operator because it doesn't have like the spectrum license.
Yeah, this is not related to license, but in the end it results in the same thing that I described here. Because if you don't have a license, then you have a core network, but you talk to the MNO, the real operator who has the spectrum license, who has the radio access network. So it's just how do you define it precisely? Yes,
yeah,
but technically.
There may be a case when you own RAN equipment, then you sub-license the spectrum license, and then you use the core network of the operator from which you sub-license your spectrum license.
Okay.
And this case you also MVNO.
Okay, well, you cannot sub-license spectrum here, so we don't have that case. Okay, well, something about billing, because that relates to Camel quite a bit and what we just discussed before. So initially when GSM was designed, it was, you always have to go back to the history, and there's this very excellent book I can recommend anyone by Dieter Hillebrand, a German guy who wrote an English book about GSM history. Actually many authors, but he's the publisher. Initially GSM was designed for radios installed in cars of business people who cross Western European borders. That's the design requirement of GSM. So the mobile station was a suitcase-sized device you put in a car, and it was intended for, let's say, some German business traveler driving from Germany to France, that he can have his seamless coverage and still use his phone while he's in France on traveling, or in Denmark or whatever. So in this case, there was no need for any prepaid payment. So GSM initially did not have any provision for prepaid situation. You have business travelers, they have large corporate accounts with telecommunication companies. So no matter how much charges they make, you can always recover it, or the risk of not recovering your investment or not recovering your money was very little. So what happened is basically each network just logs all their calls, SMSs and so on, and then they exchange CDRs, call data records. Those exchanges, they can happen at the end of the week, end of the month or something, but not very frequently basically. And then the CDR records are exchanged between roaming partners. Sometimes also there are dedicated CDR clearing houses and billing outsourcing providers and all kind of crap that the industry is coming up with. But technically, the CDR files are exchanged, and the CDR files are often vendor-specific or custom. There is a GSMA established standard called TAP. Some accounting procedures, but I don't know what the T was for. TAP, accounting procedures. Anyway, that's sort of a standard used a lot. It's also specified in ASM1, but it's GSMA standard and not 3GPP standard, and I think it's not really publicly available. So then prepaid services came around, and everybody had to have 15 different SIM cards, all of them prepaid, and not only people who have a credit line, but everyone should have prepaid cards. And now the problem is, of course, with this kind of having the inter-operator billing in a post-paid CDR exchange situation, but having prepaid SIM cards. There was, for some time, there was in the 90s, there was some way to sort of exploit that behavior. Let's say you get a German prepaid card, you go to Spain or something like that, and then make lots of calls there, and only at the end of the month they discover that you didn't have the credit for that. So there were some years where really this kind of fraud happened, but it's a long time ago. And in order to combat that, they came up with using IN, intelligent network. Intelligent network. It's very. I like the term.
But not the intelligence network.
No, not intelligence. It's intelligent network. IN, and there was first some use of INAP, the intelligent network application part. But then they developed something called CAML, which is customized applications for mobile enhanced logic. And CAML is sort of the standard for this now. There were some operators that also used USSD transactions, as you mentioned, but I don't think in Europe it was ever used. I only heard of it from, outside, but I don't think in Europe it was ever deployed. Okay, so.
But in many cases, if you travel with prepaid SIM cards to, I don't know, Asian countries or somewhere, you still have to use USSD codes to be able to make MO calls.
Yes, that's the that's the call, because they don't either they don't have CAML or they don't advertise CAML. That's two different things. So in the roaming agreements and in these IR21 forms that Dimitri had mentioned, you specify actually what kind of CAML phase you support to the other operators. And of course, technically, all the map messages, all the location updates, as we've seen, contain that information too. There is an entire hierarchy of fallback mechanisms. If you want CAML phase 4, you try to fall back on 3, you try to fall back on 2, you try to fall back on 1. If that doesn't work, you can try USSD, or you can go for bar all outgoing international calls, or this sort of this fallback of how to restrict the roaming subscriber in this case. But I think we don't really need to go there now. CAML is not just a protocol. I mean, the CAML actually is the entire system. The protocol is called CAP, the CAML application part. So if you want to say all to expand all the acronyms, it's the customized application for mobile enhanced logic application part. And CAML introduces a tremendous amount of changes into all the equipment. It's actually quite sophisticated. CAML, you see, LaTeX Beamer doesn't scale the font to the size of the line, unlike my ladder diagram tool. So you have the SCF and the SSF, the service control function, the service switching function. There is a GSM and a GPRS version of it. So the service control function is a new entity in the network, the GSM SCF. It runs somewhere close to the HLR, so in the core network of the home operator. And it controls whatever services and how services are being used by the subscriber by controlling the SSF, the service switching function, which is built into the MSC or also into the SGSN in case of the GPRS SSF. So what this means is you have built into the MSC and SGSN, you have sort of a remote set of hooks and events and triggers and state machines, that can be configured and runtime changed by the SCF, the service control function. And if you ever thought that GSM has many acronyms, then please read about Camel, because I don't think I've seen any other part of the system that has so many acronyms that are completely strange. So CSI is not a popular TV show, but it's the Camel subscription information, of course. And there are many, there's TDPs and EDPs and RDP, and actually there's one good book on Camel, and I think it contains something like a 10-page in small font kind of acronym dictionary at the end. So just to give some more information, basically what happens in a Camel-enabled network, your subscriber data inside the HLR contains CSI, Camel subscription information. There's Camel subscription information for mobile originated calls, for mobile terminated calls, for MO SMS, for MT SMS, for packet data services, for USSD, for supplemental, basically for anything you can do in a GSM network, there are Camel subscription information data records. They are again ASN1 specified. And inside the Camel subscription information, there is some configuration about which particular state transitions should cause something like a callback from the SSF in the MSC to the SCF in the home network at the time a service is used in the network. So Camel specifies call state machines, BCSMs, basic call state machines. There is an OBCSM and an TBCSM for originated and terminated call. And the state machines then contain trigger detection points and event detection points. And you can remotely arm these points, which will then generate messages from the SSF to the SCP. And the SCP can then dynamically, depending on whatever kind of decisions, even arm or trigger more of these points in the SSF, with the entire result that from the pure core network point of view, in the home network, you can basically, any kind of state machine transition anywhere in the visited network, you can make it stop, send you a message and ask for permission if it should proceed at that point. And you can even do things like remotely configure timers, especially in case of charging. You can say, well, for the next 10 seconds, continue. After 10 seconds, give me another callback, and then I can check if there still has enough credit, and then I can send back if it should proceed or not. But with the later Camel phases, you can even remotely inject voice streams, like voice announcements. Oh, your credit will expire soon in whatever is the native language of the person. And you can, of course, redirect calls, rewrite phone numbers. You can basically do anything you want using that system. But as I said, it's fairly sophisticated.
Yeah, if it were done in the internet world, it would be done in XML and called RPC or core bar.
Yeah, probably. But I mean, the protocol itself, if you have already the entire TCAP and map stack, then implementing CAP is very simple to do, but it's all the state machines on both sides. And those you would have no matter what is the transport protocol. You would have all these state machines and transitions and so on. Yeah, that's quickly about Camel. Now, what do we have in terms of implementations? I have been working over the past 2 years on some Erlang code. The reason for Erlang was not, I have to be frank, I don't like programming languages. I don't like to, I'm not one of these guys who tries a new programming language every year or so. I never really learned Python. I learned Perl in the 90s and I still use it today. Python is, okay, I can write a 2-line patch somewhere, but I couldn't write a complex application in Python. I don't know anything about Java. I can look at decompiled Java code and figure out what it does, but I don't write stuff in Java. So I'm very conservative when it comes to languages normally. But what was needed in all this SS7, especially in the higher layers, is very good ASN1 support. Not only for BER, but also if you look at other applications, especially in 3G, then there's a lot of different encoding schemes that are not BER. And I wanted to use something that is very good ASN1 support and that it has decent support, a decent abstraction for state machine implementation. And both of these aspects are true in Erlang. You have the Erlang OTP system has what's called a Gen FSM, a generic finite state machine, that you can configure, and you can more or less have a one-to-one mapping from the state machines in the specs to the state machines how you implement them. And the funny thing is there is a graph FSM module, so from your source code you can generate a state machine graph and then compare that graph with the graph in the spec.
Really?
Yes.
In OTP?
Sorry?
In OTP?
Well, no, it's an external module that somebody wrote, but still, so you sort of, I'm confident that you can, even if it's very complex code, you can at least somehow figure out relatively quickly whether it does what the spec says or not. So, Erlang is not easy to get into. I have to warn from that. You can never change the value of a variable. It's single assignment. A variable gets assigned once and you
It's
cannot
functional
change it.
language after all.
Yes, but I don't think that's a property of functional languages. But the functional part, I think it's not that okay. I mean, everyone who has worked in any of the OsmoCon projects or in the Linux kernel knows structures full of function pointers and using them in a creative way. It's, you know, it's not that different from what you do in functional languages. You pass around pointers to functions, okay, you pass around the functions themselves. The funny part about Erlang is that the function is an object like everything else, so you can store it in databases, you can send it to another node, the complete function, you know, and so that's fun, but I haven't really used that. Okay, now in Erlang we now have a couple of implementations. There's zero documentation on any of them. Some of them are commented to some extent, but there's no documentation at all, no examples how to get this working. Because I only implemented whatever was needed for a given project, and I never had any decent funding for any of that work. So Osmo SS7 does signaling link management and link set management, MTP level routing, and it contains protocol, what I call protocol codecs. A protocol codec is something that converts from the on-wire message into a nested Erlang data structure, and vice versa. So you can decode the message into something high level and you can encode it again in the other way. And there's for BSSMA, for ISAP, M2PUA, M2UA, M3UA, MTP3, SCCP, and SUA, we have protocol codecs in there. They don't do any logic, they just translate between different representations of the same data. And then we have actual protocol implementations for M3UA, M2PA, M2UA, and SUA. As well as the IPA multiplex called SCCP Lite, also in some cases. So those exist, and the protocol implementations, they actually do the link state management and whatever strange stuff that goes on. There's some state machines in the ITF specs for ASP up and ASP inactive in those states. Those are all managed in those implementations. Then there is Osmo SCCP, which is, well, sorry for that, it should be not, of course you don't use SCCP on top of Osmo SCCP, that would be an endless loop, but no, on top of Osmo SS7. It contains SCLC, connectionless, SCOC, connection oriented, and SCRC for routing and global title translations, and then you can have applications that bind onto subsystem numbers on top of the SCCP stack. The connection-oriented implementation has not received a lot of testing so far. I have established a couple of connections, but it's not really used much, so there may be dragons. Then we have Osmo Map. Oh, where's TCAP? Ah, no, Osmo Map. Yeah, okay, sorry. I'm getting confused myself. So before I was able to complete TCAP and a real map implementation, I wrote the Osmo Map code, which is not a real map, not a map implementation that people would expect. It's really the codec for an integrated TCAP and map codec. So what you can do is you can receive the ASN1 encoded TCAP and map message over the SCCP stack. You can throw it in Osmo Map, and it will expand recursively the TCAP part, the TCAP dialog portion, the map dialog portion, the TCAP component, the map component portion. So you put in one binary blob and you get one extracted, exploded structure of all the stuff inside. And then this is primarily useful for protocol analysis because the Wireshark detectors are not very good actually, and they are not automatically. They use a certain version of the spec with some manual changes, and it's not very nice. So that can be useful, but also I have written a transparent map mangling engine that you can use for doing translations in map. It's just like, I'll talk about that later. But the idea of those translation engines is that you can, it reminds me a lot of what I did in NetFilter some ages ago with FTP and IRC network address translation, where you need to go inside the PCP payload and replace some IP addresses that are somewhere in there. And that's a bit what I do with this code. So you have transparent gateway inside a signaling link. You're not an end node. You don't terminate SCCP or TCAP or map, but you just process all the messages. You go into all the layers, and then you exchange some global title or something, some IMSI inside, and then you re-encode everything and pass it on to the other end. That's sort of what this code was written for. And that's what's called MDW, NAT, the media gateway NAT. The name is sort of a misnomer, but well. You can do global title masquerading using a pool of global titles, and it will dynamically allocate new global titles from a certain range and keep a persistent state table on that. You can replace global titles inside map payload. You can support camel face patching. That means you can enable or disable certain supported camel phases depending on which operator you talk to. So some operators want that kind of feature.
And what was the goal?
The goal?
Some sort of roaming coordinator.
Well, I don't know if there is any name for what is being done with this, but basically you're an operator, you have your equipment supports a fixed set of camel faces, but then for whatever contractual reasons, depending on what home operator you talk to, you do not want to advertise that you can do camel 3 because whatever the contract says it's only camel 2 or whatever, and then if your MSC cannot configure that, you have to have some gateway to remove that. There's also ISAP global title mangling, and you can convert from different plan numbering formats inside, and this is used in production. I think it's actually more than 1 year now, maybe 2 years, but that's really used 24/7 and runs very stable. I haven't received any bug reports or any crashes or anything for a long time on this. Then we have Signal, that's Vance Shipley, a Canadian guy, developed some, I think 6 years ago, he started to write TCAP and map in Erlang. He never released the code, but he also never had time to finish it. However, his code automatically generates document, so it has something like Doxygen for Erlang, it's called ErlDoc. And the documentation was on his website. So when I googled for Erlang TCAP stuff, I found his site, but the code was not there, just the documentation generated from incomplete code. And I contacted him and sort of convinced him to release the code, and it's now under a PSD style license, and it's on the OsmoCom Git repository. And meanwhile, I have completed the TCAP implementation. It turned out to be much more things missing than I originally thought. So I would say, yeah, more than half of it was missing actually. But it's a one-to-one mapping of these ITU state machines to Erlang state machines for dialog handling, transaction state machine, invocation state machine, and then we have other entities, component coordinate, transaction coordinate. This is all the same terminology like in the specs, and they're all more or less in there. There's also the Vance wrote ANSI and ITUT, TCAP and map. But the ANSI part I have never even looked at, so it's completely bit rotten by now. Unless somebody has a need for that, it will stay that what it is. So the TCAP layer implements what's called the N primitives towards the SCCP on the lower level, and it implements the internal TR primitives and the TC primitives towards the user. So a user application uses something like TC invoke or TC result last, or some kind of these kind of primitives. They're in the spec, specified in the TCAP spec, and those primitives are used by an Erlang application that actually uses the stack. You can use it directly, or there's also a Signal map implementation, but I personally don't like it actually, because if you look at the specification, TCAP almost does everything, and the map doesn't really do much, because TCAP already gives you sort of the component portion of the stuff that you received, and then all the map does is run it through the ASN1 decoder for the map message, and that's sort of it. And the primitives are slightly different. Instead of TC begin, you have map open. Okay, instead of TC end, you have map close, and that's sort of a bit. I don't like it that much. So it is there, but all the stuff I did so far, I use the TCAP API directly. I don't really see much sense of that. Now, we don't have any complete application server for like an HLR or any other core component so far, but there's quite a bit of examples and experimentation code for manually creating single map transactions against traditional implementations. What actually exists now, and I can give people access to that, I have a SIGTRAN, OsmoCom SIGTRAN network with multiple STPs and proprietary HLR and MSC and AUC and lots of components in there. And so if you want to join that, I can configure you M2PA or M3UA or SUA links that you can connect that, and we can agree on point codes and global titles, and then you can actually talk to that HLR or that kind of stuff. So my idea is basically once we have more of these implementations integrated with our, let's say, Osmo BSC or have a real MSC or an HLR, that then people could run their own GSM network at home or in their office or something like that and connect to that, and then we could actually have roaming between the offices using GSM core network protocols. That's sort of the goal for testing that stuff beyond unit tests. So as opposed to a lot of the C implemented OsmoCom stuff, there are lots of unit tests actually in the Erlang implementations. And some of them actually use PCAP files. So you can, I don't commit the PCAP files to repositories because they're often from customers and contain sensitive data, but there is some Erlang code for opening PCAP files, and then from feeding each and every packet into the stack, decoding it, re-encoding it, and comparing if the binary is the same. So just to verify all the implementations.
This is for testing your codecs.
Yes, the codecs, but also even for the state machines, there are quite some tests. Okay, now I'm going to stop.
And do you really plan to use Nisia? Because
Yes.
I heard that people complain it doesn't scale up well, so it's a good start, it's very like nice thing, but when you want to have a real HLR, you will probably hit the limitations of Nisia.
Okay, I want to hit them. So, I mean, right now none of this Erlang code is written with any kind of scalability, right? It's just meant to be an implementation at all. And then I'll see once it's complete, once there is an HLR, then I can do some benchmarking and see how well it scales. But
Yeah, because maybe it's just easier to start with something else from the very beginning. Like people tell that like CoachDB is a bit better, or
I don't.
The creator of CouchDB just abandoned it because he says it doesn't scale. Ubuntu couldn't make it scale, so it's
okay.
No, I mean, I just wanted to use Amnesia because it's in Erlang OTP. You don't need any external packages or dependencies. It's just there. It's complete and it is distributed. So. And if that needs to change, well, then it needs to change at some point. And if even without Nija the entire stack doesn't perform well, then it doesn't perform well. So I mean, I'm not implementing this to be used. The goal is not to have an HLR for 100 million subscribers or for even for 10 million subscribers. That's not what I have in mind, because if that was the goal, then there would have to be a customer that actually has that kind of requirement. For paying something like that. It's really mostly my interest in having any of these implementations around at all, and there may be one or two smaller MVNOs that want to use this, but they don't need the scalability of a large operator.
Yeah.
So.
Anyway, when you have this working, it will be easier to scale this later.
Yeah, exactly. Premature optimization is the root of all evil.
Yeah, right. Right.
Okay, let's 3 more slides on C stuff. libosmo SCCP, I think everyone knows. It's a small SCCP implementation. I think it's far from being complete, but useful for the A interface. Holger doesn't feel offended by that.
No, it's just the codec functionality. So you
Yeah.
can create messages, pass them. and-
Yeah, but no state machines or no dealing with lost messages or anything like that. Then there's libosmo ASN1 TCAP, which is ASN1C generated TCAP codec, no manual code, built as a shared library that can be linked to applications. There is libosmo TCAP, which was my first TCAP implementation before I started the Erlang stuff. It's not complete, but I think it's actually fairly complete. I just looked at it a couple of days ago and I was surprised how much stuff I already wrote. And so it uses a lot the ASN1C generated data structures and uses the libosmo ASN1 TCAP. About the future of this I'll talk quickly after that slide on Osmo ASN1 map. That's just the automatically generated map codec from ASN1C. Again, no manual code, built as a shared library. So what's going to happen to that C code? It's a bit unclear at this point. My goal is to first finish the Erlang code base. But one of the ideas for the libosmo TCAP would be to use it from the SGSN, because the SGSN needs to talk to the HLR. And I think an MSC, implementing an MSC in another language like in Smalltalk or in Erlang or something is still feasible, but implementing the SGSN in such a high-level language is not a good idea, because it has to deal with all the user data. Right? In GSM, in the newer GSM releases, the MSC is split in the media gateway and MSC server. MSC server only has to deal with signaling. So something like that you can write in a very inefficient, interpreted, just-in-time compiled, whatever abstract high-level language, because it's just signaling. You don't care much about performance. But in the SGSN, the data path and the signaling path are together. You don't have an external media gateway, and you need to do all the encryption and decryption and the segmentation and queuing and all this processing in the user plane in the SGSN. So I think for the SGSN we will not have any implementation in anything else but C. But we still need to speak TCAP or map to talk to the HLR. So there would be a need. So either we have the SGSN in C and we have some kind of interface into Erlang to use the Erlang implementation, which I think looks like crap. I mean, it doesn't combine well. Or we have that libosmo TCAP that in C that we can use from the SGSN, but yeah, nobody knows what will happen. Okay, now, who wants to throw more acronyms at me?
I want to be nitpicking.
Yeah.
So BER encoded, I think it's wrong. It's like DER encoded and BER decodable, isn't it?
No, I think they actually say BER.
Are you sure?
I never saw distinguished encoding rules in the map specs or somewhere. Maybe in a newer release that they changed it, but maybe I just didn't see it.
I have to check again. The other nitpick is like on MTP. So there's a difference between link sets and links.
Yes.
So you hand stuff down to a link set and
Yes.
not to a specific link.
Yes. You do.
I like to-
Which the code actually also does. It's just not stated correctly.
Yeah, so for like this stack you have redundancy on various parts. So like with NTUA you can have round robin servers or application processors. And on MTP you can do the same. So you can have like up to 16 different links for a link set. It's in some ways very scalable. It's surprising how far they thought of what they do and how reliable it should be. And I think MTP2 has some kind of very strict requirement of how many bit errors per millions of messages may occur. It's
One more question. ASAP doesn't do global title translation, does it?
No.
Okay, it's just a mobile thing.
the SCCP feature and the subdoesn't with SCCP.
There are some strange use cases in the case of end-to-end signaling, but as it goes over SCCP.
Really? Okay. In Russia?
No, in Germany.
In Germany?
It was something like pre-IN implementation of IN services.
Okay, well.
So, yeah. So you plan right now to continue developing your Erlang code, and so what applications do you plan to implement in Erlang right now? You said about HLR.
That's my main goal, yeah, because it's relatively simple. I mean, if you have all the protocol stack and everything there, I mean, all you need is to store your subscriber data somewhere, and you need to look it up and implement, you know, a couple of transactions, but it's not very complex. Like in MSC, you need to care about all the calls related signaling as well, in addition to the map interfaces, but in HLR is relatively self-looking.
About 10 or 12 transactions.
Yeah. And even in some cases you can live without all of them. So that's
And when you are expecting to get some tests?
It depends also again a bit on customer interest. There are several MVNOs that have indicated interest, but there's no contract or anything. So I mean, if I'm doing it in my spare time, I cannot say when they will be finished. But if there's going to be one or two of these paid projects, then it can be relatively quick.
Maybe I'll add some time.
Sorry?
Maybe I'll be able to add paid projects and then a paid project.
Okay. Yeah, cool. So it really just depends on how much time I'm able to spend on this based on commercial interest.
Okay, and so what else do you plan to do in Erlang?
I don't have plans.
So no plans for other projects yet.
Not really, no. It depends on what kind of requirements we will see. I mean, what I would appreciate if there's anyone else with an interest in Erlang to sort of also get involved in this, because it's always bad to have a single point of failure. In that case, me being the only one who even understands the programming language in which the stuff is written. Not even to say the code, but just the language in which the code is written.
So you should have you should set up a workshop on Erlang for Osmo developers.
I'm not sure whether I would be the best person. I mean, somebody who has just 2 years of experience with the language is probably not
But
the
you
best
know,
one to.
it's you have a fresh view on the language, so it's always nice. And what about small projects?
Well, I think Holger will talk about this tomorrow.
Ah, it's tomorrow.
Do we have
Ah, okay.
a slot for them as well?
Okay.
So, how are we in terms of time? It's exactly lunch break. Oh shit! It's already it's 12. I'm misreading it. Can't even read the watch anymore. It's great. Okay. Relax. So we have something like half an hour, and then we would need to leave at 1:45 because the reservation in the Chinese restaurant is at 1. So if you